Hi, welcome to the first video in a short series of videos about the general workings of a computer. This is designed to give the novice programmer a little inside information that should make programming make a little more sense. In this video we will talk mostly about the internal structure and operation of computers and a little bit about the binary number system. The infancy of modern PCs started with the humble calculator back in the 1970s. Intel had been hired to create memory for a simple calculator, but when the Japanese company went with another company's design, Intel bought the rights back and introduced it to the world as the first ever CPU. As I said, Intel started out as a memory chip manufacturer, so let's start there. There are basically two types of memory. ROM, which is read-only memory. That means that it can only be read from. You can't write new information to the chip. The manufacturer will program it to have certain values, and then it will stay that way until it's discarded. Then there's RAM. RAM is random access memory, which means that the memory comes essentially blank, and as you're using the device you can write new numbers into it and read those numbers back out of it. ROM is generally used in small single-purpose devices, such as the remote control for your television, maybe the control panel for a microwave, but even more critical devices like ballistic missiles. The key is that they're single purpose. RAM, on the other hand, is the predominant type of memory in computers. Computers that are designed for multiple purposes. You can play a game, you can work on a spreadsheet, write a document, go onto the internet. Things are always changing, it's always doing new and different things, and so it needs memory that it can write to and change on the fly as you're working or playing. Every RAM location, random access memory location, is going to hold an internal number, either a 0 or, in this case, a 1. It also has an input-output wire, which has 3 states. In this case, it's in the off position, which is how memory spends most of its time. When it's off, it essentially is totally disconnected from the input-output wire and doesn't pay any attention to what's going on there. In the read position, the memory cell is going to read into it whatever value, 0 or 1, is on that input-output wire. And in the write position, it's going to change the value of that input wire to either a 1 or a 0, whatever's in the memory cell. Now you can't do very much with a single memory location, just holding a value of either 0 or 1. So the first PCs, introduced by IBM, made with the Intel 8088 chip, had memory stored in 8 blocks of memory at the same time, and they were connected to the central processing unit using an 8-bit data bus. The data bus is a group of parallel wires working in tandem to transmit data from one component to another inside the motherboard of a computer system, sort of similar to the ribbon wire shown in this picture here. But instead of physical wires, the data bus is made up of traces that are built right onto the circuit board. Here's the basic layout of the internal structure of a motherboard. The CPU, or central processing unit, is the brain. That's where all the action happens. It's connected to memory via the data bus, shown going along the bottom here. Notice on the data bus near the CPU, the arrows going both in and out of the CPU. This indicates that the CPU can both read and write data from the data bus. Now the CPU will select which memory location to use by the address bus, shown going along the top here. The address bus selects an address by putting numbers onto its bus. The addresses start at memory location 0 and can go up as high as however many is allowed by the bus size. The first PCs had 20 address lines. That allowed them to go from 0 to a little over 1 million memory locations. Lastly, going along the very top, you'll notice a line that's labeled R/W. That's the read-write line, and that goes to every memory location and tells it whether it's going to be reading or writing from the data bus. Let's take a little look at what the CPU has to go through to do even a simple little programming line like A equals B plus C. There are basically 4 steps that it has to go through. It has to go and get B from a memory location and store it in the CPU. The CPU then has to go and get C and store it in the CPU. It then has to add them together, and then it has to write that sum out to memory location A. Its first step is to put a number out onto the address bus, which points to memory location of the variable B. The CPU then sets the read-write line to read, meaning that it's going to read from the memory location. That tells the 8 bits to dump their information onto the data bus. Once the information is on the data bus, the CPU will read the information in and store it on one of its internal registers, which is basically like a memory location inside the CPU, where it can do math operations on them. The CPU then turns the read-write line off, so the memory location disconnects from the data bus. It then puts another address out onto the address bus. This one, it points to the variable that C is stored at. Again, it activates the read-write line to the read direction, and the memory location dumps its data out onto the data bus. Now remember, the memory location doesn't lose the value that's stored in it when it dumps it out onto the data bus. It's just that the whole data bus starts to match what's in that memory location. The CPU then turns off the read-write line, so all memory is disconnected from the data bus, and the CPU does the math problem, B plus C, and stores the answer into one of those internal registers that I mentioned. Once it has the answer, it puts out onto the address bus an address that's going to point to the memory location for variable A. The CPU then puts out onto the data bus the answer to the equation, and then activates the read-write line, this time in the right direction. And that memory location A will take in whatever on the data bus and store that number internally. And that's basically it. That's how the CPU processes even the simplest of little commands. Bear in mind that although this took us a few minutes to get through, a CPU could do thousands, modern computers, tens or hundreds of thousands of these in just a second. So they're very, very fast at doing this. Next, let's take a look at some the number systems used by computers. We all know this number, 537, is the same as adding 500 plus 30 plus 7. Going back to elementary school math, we know that the 7 is in the ones column, the 3 is in the tens column, and the 5 is in the hundreds column. This is all based on the decimal number system. That deci part is Latin, meaning 10. And that's how all of our standard math is done, based on powers of 10. What do I mean by powers of 10? That means that we have a ones column, and then as you go one column to the left, you have to multiply whatever's in that column by 10 times what's in the column to the right. So here we have a 7 in the ones column. The next column is going to be 10 times that 1, so it's times 10. The next column over is 10 times the one previous to that, so it would be 10 times 10, which is 100. Next would be 10 times 100, which would be 1,000. Then 10 times that would be 10,000. 10 times that would be 100,000, and so on up until infinity. One other thing I should point out on our number system is leading zeros. We know that if we wrote this number down with all those zeros in front of it, it doesn't change the value of the number. It's still just 537. You can have those leading zeros there and not influence the number at all. Computers don't use the decimal number system. Instead, they use binary, which instead of being based on the power of 10, like the decimal system, are based on the power of 2. So we can think of each memory location in RAM as one of the columns in that number system. We still have our ones column, but instead of going up by 10 each time, because we're in binary, we're going to go up by powers of 2. So the second column, instead of 10 times 1, is going to be 2 times 1, which is just 2. Then the next column is 2 times that, which is 4. 2 times 4 is then 8 in the next column. Then 16, 32, 64, and 128. As we know, we can only have a 1 or a 0 in each of those columns. And what we can do to convert the binary number into a decimal number is just multiply the ones by whatever column they're in, and then add them up together. So in this example, with it ending in 1011, we would add 1 plus 2 plus the 8 to equal 11. This is really no different than what we do in decimal math. Like we said earlier, 537 is really just the components of 5 times 100 plus 3 times 10 plus 7 times 1. In binary, we would have 1 times 8 plus 1 times 2 plus 1 times 1 equals 11. Of course, in that last example, we kind of skipped to the 4 column, but there's only a 0 in there, so it doesn't really matter in our addition, because if you look at it, it'd be 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. But doing the math, we see that 0 times 4 just equals 0 anyways, and adding anything to 0 doesn't change it. So we can just eliminate adding those up and just leave any zeros right out of the equation. So in this one, we have 1 times 2, so we add 2 to the plus 4 plus 8 plus 128, and that equals 142. So now the way this is set up, every single decimal number, whole number, can be represented exactly this way. If you were to go through every possible combination of this, you would see that every number from 0 to its maximum, 255, could be shown here. It doesn't skip any numbers and it doesn't add any extra numbers. Of course, that does demonstrate the problem. Naturally, we want our computers to be able to work with numbers much larger than 255. And that's where we as programmers, and we'll get into this later on, format our data so that it uses multiple memory locations to be able to make much bigger numbers. We'll get into that a little bit later. Speaking of which, throughout this whole thing, I've been using the first computer, 8-bit computer, as our example, but computers have evolved since then. Those first 8-bit computers, they could have a memory location that could hold a number 0 through 255. But it wasn't long until they came out with a 16-bit computer that could hold a number 0 to over 65,000. Nowadays, there are 32-bit and 64-bit computers. 32 bits can hold a number between 0 and over 4 billion, and 64-bit computers can hold a number from 0 all the way up past 2 quadrillion. Also, our modern memory address bus has gotten much wider. The original one was 20 bits. That could access up over a little over 1 million bits of memory, or 1 million bytes of memory. Nowadays, the Intel data bus is 42 bits wide. That can access 256 trillion addresses. This is way more than almost anybody could ever use on a home computer. Most computers sold nowadays will come with either 4 or 8 gigabytes of RAM, which is billions of bytes, and a lot of times the motherboard is designed so that you could upgrade that to about 16 gigabytes, which is about 16 billion bytes of RAM. Okay, that's all for this one. Next time we'll do a short film on the Windows operating system's file structure.